And I need to keep remembering to mute this. Okay. Now I think I'm in business. So, not quite yet. Share my screen. Okay, now I'm in business. Okay, so let's talk about polyatomic ions. Polyatomic ions, as the name suggests, is basically a collection of atoms of different elements that, okay, why is this? That's what I should have done. Right, so polyatomic ions are basically a collection of atoms of different elements, and that collection is held together by covalent bonds, and that collection is a unit which carries a charge, right? And the charge can be positive or negative. Most of the polyatomic ions that exist are negative ions, but there are few, in fact, 3 in common usage, which are positively charged, which we'll talk about shortly, all right? So that's what I just said. So you don't have to pay attention to that. I don't care about memorizing stuff because, again, I'll provide. Remember that same table I showed you the last time? You'll be provided with that table in your test and so on. So you don't need to memorize these ions. I know some instructors require people to do that, but that's not my way of doing things. There's some particular prefixes that you'll find in association with some oxygen-containing polyatomic ions, hypo and per, all right? Basically, hypo means that you have one less oxygen than the ion which does not have the hypo prefix, and per means that you have one more oxygen, right? So for example, where's the, oh. So, okay, so for example, let me do it up here. Okay, what's going on here? Oh, why is this thing not writing? Come on. Oh, okay, there it goes. So ClO4 minus, this is known as the perchlorate ion. ClO3 minus is known as the chlorate, all right? So basically the perchlorate will have one more oxygen compared to the chlorate, all right? And then hypochlorite, well, let me just say that, let me do it down here, or over here. ClO minus is known as it. In fact, I think, let me not go through all that. Okay, I think I have some of them here actually. I forgot about it. Okay, so this is the chlorate ion, right? And this is the perchlorate. So as you can see here, the perchlorate has one more oxygen compared to the chlorate, I'm sorry. All right, and then now the ClO2 minus here, this is known as a chloride ion. And then the hypochlorite ion will have one more oxygen, one less oxygen compared to the chloride ion. So hypo basically means one less oxygen, per means one more oxygen, right? But you don't really need to know all that. Those are just some patterns in the naming that we can correlate to the actual structure or composition of the ion. All right, so this list here is basically a list of some common polyatomic ions. And when it comes to using these in formulas, you have to be careful because you need to indicate the fact that you're dealing with a polyatomic ion in their formula. So for example, you notice that in this compound here, that is known as calcium hypochlorite, right? And you'll notice that the chloride ion formula is surrounded by parentheses, and then you put a 2 outside as a subscript, right? So basically what we're saying is that if you have a formula which contains a polyatomic ion, or I should say contains more than one polyatomic ion in the formula, you need to put that within parentheses and then put the number of those ions outside as a subscript. And you see other examples like, well, I don't see any more, oh, like this one here. Now, in this case, we're dealing with ammonium, which is a positive polyatomic ion. It's the only one listed here, but there are others. You have the hydronium, and these are all in the table that I gave you in Canvas. This is known as a hydronium ion. That's another positively charged polyatomic ion. And then there's this one. And this might seem weird in terms of the name. This is called mercury 1. Now, you might be wondering, why is it mercury 1 when we have a 2+ here, right? Well, the answer is that this ion is diatomic, right? So basically, overall, there are 2 atoms that make up that particular ion that carries a 2+ charge, which basically means that there's a charge per ion or per atom that is present in this structure. Before, it was thought that mercury 1 had this structure, Hg+. And then somebody did some intensive look into the actual structure, and they found out that there's actually 2 atoms of mercury present in that ion. So therefore, that's why it's called mercury 1, all right? So at this level, the positive ions that are polyatomic that you will encounter would be the ammonium, the hydronium, and the mercury 1 ion, right? Most of all the other polyatomic ions are negatively charged, all right? So understanding that, you should be able to answer these questions. So the first question says, write the formula for 2 compounds, one of which is sodium sulfide. So what you do is go to the tables and you look up the formula for sodium, which is Na+, right? And then you look up the formula for the sulfide ion, which is SO3 2-, right? And the principles that we used in the case of binary ionic compounds would be the same that we would apply to coming up with the formula for this compound. In other words, you have to make sure that the total number of plus charges is equal to the total number of negative charges, right? So of course, that means that in this case, you'd have to multiply this by 2. And therefore, when you put this together, this becomes Na2SO3. All right, so that would be the answer for the A part, right? Okay, so what would you say is the answer for the B part? Now, in order to do these questions, you have to have access to the tables. You can bring it up on your devices and look up the formula for the different ions that make up ammonium sulfate. So what's the formula for the ammonium ion? Let's start off with that. NH4 plus. And what's the formula for the sulfate ion? SO4 2-. Okay, good. So what do we need to do in order to ensure that the charges cancel out?
Put NH4 in parentheses and 2 on the outside.
Exactly. NH4 and then 2 outside the parentheses, followed by SO4 2. SO4, right? Because you need to multiply the ammonium by 2, right? Please note, I don't know if I stressed this in the examples that we looked at last time. Whenever you put together the final answer, there should be no charges in the final answer. The charges only belong to the ions when you're getting to the point of solving the problem. Okay. And these scammers just don't stop calling. Okay. What would be the name of NaCN? So again, you need to go to the table and try to figure that out. So what's the answer for A?
Sodium cyanide.
Sodium cyanide. Very good. And this is a substance you don't want to drink. Anything containing cyanide, unless you're contemplating suicide, but otherwise you don't want to drink that stuff. All right. MgClO4 2. What's the name of that compound? Magnesium perchlorate. Exactly. Okay, so that's basically how you name those compounds. All right, any questions about naming compounds with polyatomic ions? Any questions? Any questions? No questions? Okay, so let's move on now to a discussion of a special group of compounds. Now, I doubt very seriously you'd have met this in your high school or introductory chemistry. So I'm going to be a bit slower in talking about the special group of compounds known as hydrates. What are hydrates? Hydrates are basically ionic compounds that has, as a part of its composition, a fixed number of water molecules associated with the ions that are present in the ionic compound, all right? Now, when it comes to naming hydrates, basically, you name the ionic part just as you would, just as we have been doing all along, but you have to add something else. You have to add a prefix representing the number of water molecules followed by hydrates. And the prefixes we're talking about is the same as what we discussed when it comes to molecular compounds. Mono for 1, di for 2, tri for 3, and so on, right? So in terms of the formula, how do we write the formula for hydrate? Well, basically we write down the formula for the ionic part, and then we put a dot, and then we put the number of water molecules. So here are a couple of examples, right? So in this particular hydrate, you have BaCl2, then dot, and then 2 water molecules, right? And the name of this compound, excuse me, is barium chloride dihydrate, all right? So the barium chloride is this part here, of course, and the dihydrate because you have 2 water molecules present, right? And please note, because for some reason students tend to, when they meet this for the first time, they tend to get confused. The dot doesn't mean multiply. You see what I'm saying? So if you're calculating the molar mass of all of this, you have to add up the barium plus the 2 chlorines plus whatever the molar mass of water multiplied by 2, right? And then you add them all together. So the dot does not mean multiply. Some students, for some reason, confuse the dot as a multiplication symbol, all right? Here's another example, CuSO4 dot 5H2O, right? And the name of this compound is copper 2 sulfate pentahydrate. Penta because you have 5 water molecules, all right? So that's basically how hydrates are, how you write down the formulas and how you can determine a name based on the formulas or vice versa, all right? Okay, so that's basically what hydrates are. So this is an example of the copper 2 sulfate hydrate. The thing about hydrates is that it's very easy to remove the water from the compound. So basically, what happens, we're going to use the CuSO4 5H2O example. Oh, and by the way, going back to this, something I need to say as well, very important. There is no way of predicting the number of water molecules that will be formed along with the ionic part, right? The only way you can determine this is by experimentation. You have to actually carry out an experiment to determine whether or not you have 2 water molecules in the case of this compound or 5 water molecules, all right? So you cannot just, it's not like naming or writing down the formula of just copper 2 sulfate, right? You just simply cannot determine the number of water molecules in the water part. All right, so going back to this, I was saying that it's very easy to remove the water from any hydrate. All you have to do is heat it to 100 degrees Celsius, and you end up with the copper 2 sulfate without the water. And the hydrate, of course, is this here. And the compound that is formed, which is formed after the removal of water, we call this the anhydrous form. All right? In some textbooks, they call this the anhydrate. So anhydrate or anhydrous, same thing. I tend to use anhydrous because that's what I've learned initially, all right? Very easy, right? All you have to do is heat the hydrate, and then you end up with the anhydrous form. And it's also very easy to reverse, right? In other words, if you have the anhydrous form and add water to it, you're going to get the anhydrate form, all right? And that is what is being demonstrated here. This is the hydrated form of copper 2 sulfate, right? And this is the anhydrous form, right? So you'd have to heat this to 100 degrees to get the anhydrous form, and then to get back the hydrated form, all you have to do is add water to it, and it turns back into the hydrated form. Now, obviously, as you can see in this example, there's a change in appearance, right? the hydrated form of copper 2 sulfate is blue, while the anhydrous form is white, right? But that is not always the case, right? In fact, I would say in most instances, the anhydrous and anhydrate forms would also be white. For example, in the case of, where am I going to squeeze this? All right, tell you what, let me just erase this here. In the case of the barium chloride example, in the case of the barium chloride example, both the anhydrous and anhydrate form are white in color. So in the case of barium chloride, it's barium chloride dihydrate. Heated to 100 degrees, and you end up with the anhydrous form. All right, so they're both white. There won't be a color change. However, there's still a change in appearance because the hydrated form is more crystalline in appearance. So if you were to look at it closely, you'll see some crystalline granules, kind of shiny looking granules, while the anhydrous form would be more powdery in appearance. All right, so even though there may not be a color change, there would still be a change in appearance where the hydrated form, and this is true for pretty much all hydrates. The hydrated form would be more crystalline and the anhydrous form would be more powdery. In a few cases, as in the case of copper 2 sulfate pentahydrate, there's a color change, right? Copper 2 pentahydrate is one example. Another example, let me just give another example here of one that actually changes color. Cobalt chloride hexahydrate. When heated, this is actually pink in color. And when heated, forms a blue colored compound. So in that case, there's an obvious color change. But in most cases, there's not. It's just white to white, but there's still a change in terms of the hydrated form being more crystalline and the anhydrous form being more powdery. Okay, so enough of hydrates. For those of you enrolled in my lab, anybody, are you? Okay, right. There's one experiment where you'll be actually working with hydrates, where the aim, if I remember correctly, is to determine the percentage of water accurately. Okay, and by using that, you can identify what your hydrate is. Anyway, so that's basically hydrates. Now, the next group of compounds we're going to discuss, and I'm quite sure you'd have met this before, are acids and bases. So we're going to talk about acids and list some properties of acids here. And the first one is they tend to taste sour. Now, that does not mean that you need to be tasting acids in the lab to figure that out. We have other more safer ways of doing that, of testing acids. But actually, you would have consumed acids if you consume like oranges, any citrus fruits, right? That sharp sour taste, that's due to citric acid in the case of fruits, and also vinegar, right? Vinegar is basically a dilute solution of an acid known as acetic acid, about 5%. And if I'm not mistaken, you guys in the lab will also do an experiment with vinegar, if I remember correctly, where you're going to determine the percentage experimentally of commercial vinegar. Okay, so that's one property of acids. The second property listed here is that, and again, this is something I would recommend that you try to do in the lab. If it gets on your skin, especially the stronger acids, then there might be a stinging or pricking sensation, all right? And that's because, especially the mineral acids like hydrochloric, sulfuric, nitric, chromic, those are caustic acids, all right? So you don't want to get those on your skin. Now, another property listed here is that they turn the color of a substance known as litmus from blue to red, right? So litmus is a substance, and one form of it would be a solution. Another form is where you have a paper which is soaked with the litmus. And basically, if you want to test if a solution is acidic, you have to choose the blue form. You dip it in a solution, becomes red. You know that it's acidic, all right? A fourth property, and this is not true for all acids and not true for all metals that react, that we try this with acids, it says here that acids react with many metals to produce ionic compounds and hydrogen gas. That is true for most, but not all. And not all metals will undergo this reaction. The more active metals, namely the group 1 and 2 metals, will undergo that reaction with strong acids like hydrochloric, nitric. Well, not nitric, because nitric produces not hydrogen, but water. And as I said before, not all metals. So for example, copper does not undergo that reaction with hydrochloric acid. So it all depends. And if you have to do Chem 2, we're going to learn more about why is it that some metals will not react with acids and other metals will. Final property here is that acids will react with bases, and therefore, by doing that, they will lose their acidic properties. And what you're going to see is that bases are basically considered to be chemical opposites of acids, right? So there are some substances that are acidic, there are other substances that are basic, but when they combine or react with each other, then basically the resulting products will be neither basic or acidic. They will be considered to be neutral. So there are some other properties of acids which I won't get into right now, but these are the general ones that one can observe easily. So as I said before, the bases are considered to be chemical opposites of acids. So let's look at some properties of bases. First one here talks about tasting again. I would not recommend that you do this in a lab, but they tend to taste bitter, all right? Another thing I would recommend practicing in a lab is getting some on your skin. But what you'll notice is that if you do get some on your skin, especially between your fingers, then it tends to feel slippery or soapy. Now, the reason why that happens is because there's an actual reaction between the base and the oils that are produced by your skin. And the result of that reaction, believe it or not, is soap. So that's the reason why it feels slippery and soapy, all right? And then we talked about litmus again. In this case, in the case of bases, the base will basically turn red litmus to blue. So if you want to test a solution to make sure it's basic, you take red litmus paper, dip it into the solution. If it becomes blue, then you know that your solution is basic. And then the final property here is that bases will react with acids, as we said before, and as a result, the resulting products would be neutral, all right? So that's just basically a simple comparison between acids and bases. So now we're going to get into the actual definition of acids and bases. And if you want to determine or know what the definition is, the answer is, it depends on who you ask. Now, this guy by the name of Arrhenius, I think he was the first person to come up with this definition, or with a definition of acids and bases, right? So according to the Arrhenius definition, an acid is a substance which, when added to water, produces hydrogen ions and anions, all right? So any substance which, when added to water, produces hydrogen ions are considered to be acids, according to Arrhenius. And then, according to Arrhenius again, a base is a substance which, when added to water, produces hydroxide ions and cations, all right? So according to Arrhenius, an acid is a substance which produces hydrogen ions. When added to water, a base is a substance which produces hydroxide ions when added to water. And then according to Arrhenius, neutralization is a process of which an acid will react with a base to form water and a salt, right? And the formula for the salt is based on the formula of the acids and bases involved. In fact, as stated here, a salt is a combination of both the cation from the base and the anion from the acid. When they come together, they form a salt, all right? So just to give you an example or two, let me get out of this here. And let me see if I can pull up Word. Right on. Okay, so for example, I'm going to start off with a simple example of hydrochloric acid and sodium hydroxide, right? Now, firstly, you know what, let me erase this. Let me talk about the definitions first. So according to Arrhenius, an acid is a substance which, when added to water, produces hydrogen ions and chloride ions. Well, in this case, chloride ions, right? But it's the hydrogen ions that is produced, which makes this an acid. All right? And then a base, like sodium hydroxide, when added to water, produces sodium ions and hydroxide ions. So in the case of sodium hydroxide, that's what makes it a base. In the case of hydrochloric acid, that's what makes it an acid. Now, the neutralization reaction between these two is the following. Sodium hydroxide plus HCl. Okay, why did that happen? All right, I'll try to work with that. Forms. Okay, so one of the products of this reaction is water. And that water is formed as a result of the hydroxide from the base combining with the hydrogen from the acid. And that's how the water is formed, right? Whatever is left will combine to form the salt, which would be the sodium and the chloride, and that would be the salt, right? So this is the acid, this is the base, and this is the salt, all right? So the salt is formed as a result of the reaction between the two. And just to give another example, let's say your base is calcium hydroxide, and let's say your acid is HNO3, nitric acid. So in this particular case, again, one of the products would be H2O. The other product would be the result of the calcium coming together with the nitrate. And the formula, of course, would be Ca, open parentheses, NO3, 2, all right? So, of course, to balance this, we're going to need a 2 here and a 2 here, and that would be the equation for that reaction. So again, this is the base, according to Arrhenius. This is the acid, and this would be the salt, all right? So that's basically the neutralization reaction that was referred to in the PowerPoint, all right? So, and as again, as I said before, this reaction is called a neutralization reaction because basically what will happen, at least in theory, is that the properties of the base will cancel out the properties of the acid, and therefore you're going to end up with a salt, which should be neutral. And the reason why I say it should be because in actual fact, sometimes the salt can be acidic or basic. I won't go into that right now because that's another topic for Chem 2. But the whole idea behind the neutralization reaction is that the product is neutral compared to the acid and base, which combines to form, all right? The water is definitely neutral, but sometimes the salt is not neutral. In other cases, it can be acidic. In other cases, it can be basic. So we won't get into that complication right now. All right. Okay, going back to the PowerPoint. So that's what we just covered. So, okay, so naming acids. All right, so when it comes to naming acids, there's several approaches. The approach that I would take when it comes to naming acids is that we look at binary acids first, and then we look at what we call oxyacids, meaning acids containing oxygen. And then there's one particular acid which does not fall into either category, which I'm going to talk about. So this is just showing you a list of common acids and their names. So what I'm going to do is spend some time talking about how do we derive the names of acids. So let me go back to my word thingy here. Let me make this a bit bigger. And let me erase everything. Okay, so let's talk about binary acids firstly. Binary acids, right? So binary acids are basically acids which contain hydrogen and a non-metallic element. All right? So how do we name binary acids? So to name binary acids, we first mention the hydro part of it. So all binary acids start with hydro. Then the stem of the name of the nonmetal, stem of nonmetal name. And then we follow that up with ic acid. All right. So basically, this is how we go about naming binary acids. All binary acids start off with hydro, then the stem of the name of the metal that's associated with it, and then ic acid. All right, now let me give one or two examples. So there's this compound known as HCl. Now HCl, if you were to name this before adding it to water, it's a gas. The name of this compound is hydrogen chloride. All right, now let me just say something about this before I move on to the name of the corresponding acid. So whenever you have hydrogen bonded to a non-metallic element, right? Some of the rules that we covered concerning binary molecular compounds will not apply here, right? Because you'll notice, for example, there's no prefixes in this, right? And that is basically one of the rules concerning hydrogen, how should I put this? Hydrogen compounds would contain nonmetals, all right? So hydrogen chloride would be an example of that. There's no prefixes, so the name is simply hydrogen chloride, not hydrogen monochloride, all right? So that's the name of this compound in its gaseous state. Now, if you add this to water, you're going to end up with HCl, aqueous. And the name now of this compound follows the rules that I just mentioned up here. You start off with hydro, and then the stem of the name of the nonmetallic element, which is chlor, and then end with ic acid. All right. So the name of this compound is hydrochloric acid, right? And this is only after you add the hydrogen chloride to the water, right? So this is not considered to be the acid per se. This is just hydrogen chloride. But when you add it to water, it becomes hydrochloric acid. Okay, here's another example, H2S, all right? Again, it's a gas, and this one is an awful smelling gas. This is basically what you smell when eggs rot, you know that odor, right? Well, that odor you detect is actually hydrogen sulfide, right? Which is the name of this compound, hydrogen sulfide, all right? So as you can see, again, no prefixes used. It's simply hydrogen sulfide. If you add this to water, it becomes hydro sulfuric acid. All right? Hydrosulfuric acid. Okay, so that's basically how you name binary acids. They all start with hydro, the stem of the name of the second element associated with it, and then they end with ic acid. All right? Okay, so if I gave you this, HBr gas, what's the name of that compound? Based on what we covered just now. Let me just erase all of this here. Hydrogen bromide is indeed correct. So hydrogen bromide. Okay. So after adding this to water to form HBr aqueous, what would be the name of the resulting solution? Again, based on what we discussed just now, what would be the name of the resulting solution? Hydro, right? And then what? No, not bromeric, bromic. Acid. And that's it. All right. Okay, here's another example. H2SE aqueous. No, gas, I'm sorry. All right, what do you think the name of this compound is? Before you add it to water.
It's SE, right?
Mhm.
Hydrogen selenide.
Hydrogen selenide, you're correct. Okay, so after adding it to water, it becomes H2SE aqueous. So what would you say the name of this compound is? Or this solution? After adding it to water. Hydroselenic acid. You're indeed correct, my dear lady. So that's basically how you name binary acids, all right? Okay, very good. So that's one group of acids. Now, the other group of acids we're going to talk about, let me get rid of all this here, are the oxyacids. And as the name suggests, these acids, write this down, oxyacids. And as the name suggests, these acids contain oxygen, right? So let me put contain oxygen, all right? How do we name these acids? Now, there are a couple of approaches. Now, this is the approach I prefer to take when it comes to naming oxyacids. We start off with the name of the anion. So the corresponding anion, right? So we start off with the name of the anion. And I'm going to use an example here. So let's say the anion ends with, well, let me give a general and then get more specific. Let's say the name of the anion ends with ATE. All right, 8. Then the name of corresponding acid ends with ic acid. All right. So you start off with the name of the anion. If the name of the anion ends with ATE, then the corresponding name of the acid ends with ic acid. Now, if the name of the anion ends with ITE, ite, then the name of the acid ends with OUS acid. All right, and I'm going to go through some examples, but I want to just give you an outline of the rules for naming oxyacids. All right, so if the name of the anion ends with ATE, then the name of the corresponding acid ends with ic acid. If the name of the anion ends with ITE, then the name of the corresponding acid ends with OUS acid. All right. Okay, so let's start off with this example. Let's say we have, I'm going to construct a little table here. So in this column, we're going to have the corresponding anion, and then we're going to have the acid, right? So what I'm going to do here is write down the formula for the nitrate ion, right? Where am I going to put the name? All right, let me construct another column here. So the name goes here, right? No, hold on. All right, let me not bother with that. So this is called a nitrate ion. I'm just going to put the name below here, all right? That's a nitrate ion. Now, to get the formula for the corresponding acid, right? Whatever the number of negative charges here, you have to add the same number of hydrogen ions, right? So in this case, you have one negative charge. You add one hydrogen ion to it, and you get the formula for the corresponding acid. All right? So how does that change the name? Remember what we said here. If the name ends with ATE, in the case of the anion, then the name of the acid ends with ic acid, right? So in this case, this ends with ATE, the nitrate. So the name of the corresponding acid is nitric acid. You see what I'm saying? So that's how you get from the anion in terms of the formula to the acid, and the corresponding name change from nitrate in this case to nitric acid. Okay. Any questions about this? Any questions? All right, let me erase this here and give another example. So the other example I'm going to give here is SO4 2-. The name of this ion is the sulfate ion, all right? So the name, or I should say the formula for the corresponding acid. Now remember what I said. Whatever the number of negative charges that you have here, you add the same number of hydrogen ions. In this case, you're going to add 2 hydrogen ions because you have a -2 here, which means that the formula for the corresponding acid would be H2SO4, right? So the name of the corresponding acid would be sulfuric acid. All right? And that's how you do that. Okay, so that's how we deal with acids, or I should say acids which ends with ic acid, formed from anions which end with ATE. All right, now let me get rid of this here. Oops. All right, so again, we're going to start with acids. I'm sorry, anion to acid. Now, in this case here, I'm going to use HNO2. The name of this, no, I'm sorry, not HNO2, I'm sorry. I should start off with the anion name first. So that would be NO2-. The name of this ion is the nitrite ion. All right? To get from the anion to the corresponding acid, in this case, we add 1 hydrogen ion because you have 1 negative charge. So the formula for the corresponding acid would be HNO2. All right? So remember what we said here. If the name of the anion ends with ITE, the name of the corresponding acid ends with OUS, right? So this is called a nitrite ion. So the name of the acid that is formed would be nitrous acid. All right, everybody see that? So that's how we deal with naming anions. Well, firstly, that ends with ITE, naming the corresponding acid, and their names end with OUS acid. Let me see if I can squeeze in another example down here. SO3 2- is known as a sulfite ion, right? So to convert this to the corresponding acid, we add 2 hydrogen ions to get H2SO3. So the name of the corresponding acid is sulfurous acid. All right? So that's basically how we deal with oxyacids. If the name of the anions ends with ATE, then the name of the corresponding acid ends with ic acid. If the name of the anion ends with ITE, then the name of the corresponding acid would be ending with OUS acid. All right. So we dealt with binary acids, we have dealt with oxyacids, but there's one particular acid which is kind of unique. So let me just erase all this here and deal with that particular acid. Now, there is a gas known as, well, that's a formula, and this is known as hydrogen cyanide. And this is something that you certainly don't want to inhale, for the same reason why you don't want to drink anything containing the cyanide, right? So this is a poisonous gas, all right? If you add this to water, it becomes HCN aqueous. And the name of this acid is hydrocyanic acid. Now, the reason why this is a bit unique is that it's not an oxyacid and it's not a binary acid either, right? So, you know, the question becomes, well, what rules do we apply? And what the powers that be decided is that we treat this, for the purpose of naming, we treat this as a binary acid, even though it's not. You see what I'm saying? Because it has 3 elements. So basically, like, you know, hydrobromic and hydrochloric, then we call this hydrocyanic, even though it's not binary. So that's kind of unique compared to the other acids that we talked about. All right. Okay. Any questions about naming oxyacids and this acid? Any questions? Any questions? Okay. If I'm not mistaken, this is actually the last topic in this chapter. Let me check and make sure. Okay, so this is just basically what we just covered. So that's basically it. So now, in your assignment, let me see your. Okay, so now you should be able to do. Let me work it hard. Okay, so now you should be able to name these acids on page 11. Well, the first part is that they give you the acid and you're asked to write the formula, and then you're to do vice versa. So let me see what's over here. Okay, so this is now just a combination of all the rules that we have learned concerning naming compounds, binary, molecular, whatever. Same thing on this. Right, so now you should be able to complete the rest of this, right? So I want you to complete it. If you have any questions, I'm here to answer any questions if you're encountering any difficulty naming any of these compounds.
I did have a question on what we already did. So for this one, when I was reading about you and reading your notes, they say to name the one that comes before the periodic table. So when I was looking at this one, the nitrogen comes before the sulfur. So would it be the tetrasulfur or would we have to reverse that?
No. Remember what the rule says that the one that is to the left and down would be hold on, let me see.
Because they said left, top, and then bottom right.
Oh, okay. So the sulfur would take precedence in terms of the name.
Okay.
Because it's down, even though it's to the right.
Even though it's to the
Yeah,
right.
exactly. In actual fact, it's the electron, let me show you something. It's the electronegativity. The actual rule is electronegativity. If you go to, and I would use that rule when it comes to these situations. If you go to Canvas, hold on. You'll see that sulfur has a lower value compared to nitrogen. Where's that table?
So all the way bottom,
Right, okay, so sulfur is 2.5, nitrogen is 3.0, right? So because sulfur is lower than nitrogen, then sulfur would appear first in the formula and in the name. All right?
Thank you.
All right. I'll be right back.
I'm gonna go after, after my big class. Next, next semester, next period, yeah. I have like 45 minutes between tray and then lab today, so I'm gonna print last week's lab so I can fill that out and send it to them, and then have the handout for today, and then print out chapter 2 because I forgot to get home.
Yeah. Yeah, I was working for this. I was excited. I was like, oh my God, question. Then I'm like,
table, please.
I was like. It just keeps going. I know, I was thinking about it.
Yeah. Are we gonna, we have to hand this to them today, right?
The part chapter one.
Yeah.
I don't know, Rose skipped out.
It's so funny. It is so hilarious.
Yeah. Did you want the first packet, chapter one?
Well, I anticipate you won't be able to finish it today.
Well, that one's chapter two.
I mean, chapter two. Oh, chapter one. Yes, I'll take chapter one, actually. Thank you. But for chapter two, hold on, let me see it. Oh, I'll take it now. For chapter two, I'm going to set a date for this. For its due, on Thursday. Because I want to get it back to you ASAP. I'm giving you the option of turning it in online if you prefer to do so. So you can upload it. Hold on, let me publish it here first. Right, so you can upload it into Canvas if you so prefer. If you choose to do it that way, make sure that it's in the form of a PDF document, all right? Because for some reason, Canvas can deal with other types.
I will see you in lab. I'm gonna go print out my worksheets and stuff.
Yes, ma'am.
We're doing the quiz today.
Yes, it's in the quiz.
Is it multiple choice or is it written?
Multiple choice.
Okay.
Multiple choice.
I guess if you have one more question for you. For this one, I know you said today that you don't break the charges at the end, but this one is asking the specific.
Oh, that's the charge.
So that is,
What I
okay,
was talking about, the
Like-
situation, you ask somebody know the form for the compost.
okay,
So in the end, you don't put the charges in that form.
so for like this one, we wouldn't break the charges. Is
No,
it
no,
typical?
yeah, that will be charged. No, the chlorine, that should be an L, not an I.
Okay.
ClO39, right? But that's fine, the charges are fine.
Okay, just wanted to make sure I
Yeah.
wasn't,
It's only when you're asked to write down like the full formula for the compound itself,
okay,
then the charges will not be indicated.